So here's a true or false question. The matrix 1, 2, 3, 0, 0, 0, 4, 5, 6 is non-invertible. So try to answer this, and I'd like you to come up with an explanation that's done by inspection. So by just looking at the matrix, can you tell if it's non-invertible? Pause the video and try to answer. So if you've answered that it is true that it's non-invertible because there's a row of zeros, you're perfectly correct. So you can write that as our first solution. So this is solution number one. Solution number two involves linear transformations, and this is the one I wanted to show you. Maybe it's less obvious at first, but once you start getting used to using linear transformations to justify things which involve matrices, it's actually pretty cool, and it gives you, again, a geometrical insight to this problem. So let the matrix be the standard matrix of the linear transformation T of x equals ax. Now, one thing to realize is that when you're going to do a times x, on the first line you'll do 1 times x1, 2 times x2, 3 times x3. That's going to give you some number. But when you do 0 times x1 plus 0 times x2 plus 0 times x3, the second component is automatically 0. The third component is some number. So what you can see is that since the y component is 0, this vector here stands in the yz plane. In the xz plane. xz plane. So to illustrate what's going on, you've got your linear transformation. It takes a vector x, applies linear transformation t. The image is ax, and this is in the xz plane. It could be the entire plane. In fact, it is. You can check. It could be a line in that plane. It could be just a point, and in this case it would just be the point 0. But the important thing is that this is of dimension less or equal to 2. In fact, it's of dimension 2 because it's the xz plane, which is something you can check by looking at the span of the columns of A. You can see that span has a basis of basis with 2 elements, so it's of dimension 2, so it's a plane. And the initial space was of dimension 3. And it's not possible with a linear transformation, again, to go back from a space of dimension 2 to a space of dimension 3. So we'll write, it is not possible to come up with a linear transformation, which would be the inverse transformation we're looking for, which doesn't exist. That maps a space of dimension 2 or less to a space of dimension 3. Therefore, the matrix is non-invertible. So maybe one thing I'd like to add, and maybe it wasn't clear before, and I've used this argument many times, the fact that linear transformations, if you have a line, then it's mapped onto a line. Well, that I guess it is clear because I've mentioned it many times. But if it's a plane y, can't you map a plane onto R3? It's basically for the same reason. So maybe if I take 1 minute here, if I have a point, you see an linear transformation will map that point onto another point. So for example, if it's a0, then through the linear transformation, it's mapped onto some other point, ax0. If it's a line, it would mean that it's any linear combination of a a vector v, let's say kv is, and that's a line running through the origin. If it's mapped through the linear transformation, well, it's going to be kv. And using properties of linear transformation, that's k t of v, that's a vector here, so that's another line, right? So any multiple of tv generates a line running again through the origin. So lines are mapped onto lines, and it's the same for planes really, because if you have a plane, in that case you have a linear combination of maybe two vectors u and v that are non-parallel. If you apply t to this vector here, okay, t of kv plus lu, you're gonna get k t of v plus l t of u. So once again you've got a linear combination of two vectors. So if those two vectors tv and tu are linearly independent, then you're gonna be mapping a plane onto another plane. If they are parallel, you're going to be mapping a plane onto a line. But so the moral of the story is that the dimension can only decrease, it cannot increase. So if we go back to our proof, if I have a space of dimension 2, when I apply any linear transformation to it, the dimension of the image cannot be of dimension 3. It cannot be greater than 2. It could be of dimension 1. It could be of dimension 0. But it cannot be of dimension 3 for sure, because the dimension of the space can only decrease. It cannot increase. So that's why you can't go back from a space of dimension 2 to a space of dimension 3.